The discussion today is to help you guys get ready for Midterm 2. In last discussion, we talked about inductance, capacitance, RL, RC circuit, and some check your understanding question and exercises. And feel free to check it out when you have time. And today, we will give a quick review over chapter 3, chapter 4. Yes, and some tricks to get more points in Midterm 2. Because, last time the time is so short and we have so many questions to go through. And I noticed that some of us just write down on the answer sheet that, sorry, I have no time. If I have time, I will solve with step 1, step 2, step 3, but they have no time to write down their answers. So to avoid such situation happen again, I will share some tricks with you from the perspective of graders. Okay, so let's start with the review. And notice here is that we will not going to test on these sub chapters, 3, 6, 7, 8, and 4.6. You can take a note on that and avoid spending too much time on these chapters. Okay, so we will have 6 questions in the midterm 2. And each of them is very specific to check your understanding on some knowledge. So the first one is to compute the equivalent capacitance, just like an exercise on equivalent resistance in midterm 1. So we all know that in series, maybe we know, maybe we don't know, but whatever. So in series, it is just like the form of the resistance in parallel, and its parallel equivalent capacitance is just like the equivalent resistance in series, right? So it is easy to remember, just converse. But the things will seem a little bit complicated in exercise. So here is a check your understanding exercise, and feel free to unmute yourself and participant. So here we have 6 capacitances in the circuit, and we have A, B, C, D, E, 5 terminals. And I want you guys to think about what should be the CAB and what should be the CDE. So this exercise is exactly the same layout as the one in our midterm 1. The first thing I noticed that some of us may not understand what does it mean by looking from which terminal. So looking from terminals, for example, for terminals A and B, means that we only care about the things happened between A and B. And the between, the word between does not mean only these elements between A and B. It means that we need to consider all the rest of the circuit from the perspective of these 2 terminals. So the best practice you can do is to redraw the circuit. And as you've seen below in the, all right, never mind. And you see that the C is hanging out outside. So we don't care about it because we are looking for an A and B. Similar for the terminals D and E, right? You see that the electrons are running in the while, and they don't care about the C3 and the C4 here. So our answer will be clear now. So CAB equals to first C1 in parallel with something. And within the rest, we have C5, C6, and C2 in series, right? I hope this is clear for you. And give me some feedback. You can unmute yourself and say yes, anything. Right. So so we just need to replace this part with the equations we have before, right? And for CDE, it is a little bit harder. Um, because we have D and E in the middle, right? But imagine that you can drag this end, and then you put it out, you drag it to the left. You'll see that because the other end of the C3 is basically connected to C1, right? It is an equivalent node as node A. So we'll see that if we drag the D to the left, this it is connected to C3, and the other end of C3 is connected to A. Similarly, the other end of C4 is connected to node C, right? And between node A and node C, because B is not connected to anything, so we have 4 capacitance between them, and C1, C2 in series, C5, C6 in series, and each of them forms a parallel relationship. So that we can equals to, let's take this as a whole, and we know that it should be C3 in series with something. Okay, so a notation. The plus here means series relationship. Does not mean that I literally plus them together. So this part should be C2 and 1 over 6x. All right. And yeah, so C3 plus C4 plus something here. And we know that C1 parallel with C2, C5, oh, sorry. Okay. And then you plug the equation here into our draft. So don't write the plus in the answer sheet because it will cause confusion. It's my bad. So the final expression should be something like this. And let me leave it blank. Okay. And similar things happen to equivalent inductance. Actually, it is the same as resistance. So just be careful and patient and get it done. Okay. Please interrupt me if you have any questions. If you don't have, I will keep move on. Okay.
Can you explain the second one again? How you pulled it out for the
Hi,
terminals?
Navid.
Hi.
Thanks for the question.
Sure.
Yeah. So you just need to use some imagination. Like, you know, here, C3 is connected in this way, right? So if we drag on the D node and we try to drag it out here, so it would be same as this, right?
Yeah.
Right? If you ignore this part, you put it on the top, right?
Mm-hmm.
And then you just keep dragging it. Dragging it. Extend the wires. So you'll see that now it looks the same as this layout, right? It is connected to A. And between A and B, there is a C1. Between B and C, there is a C2. Does it make sense?
Yeah, I just have trouble saying it. Like, but yeah, your explanation made sense. I'll have to take another look after.
Sure.
Thank you.
Yeah, to avoid confusion, you can erase the part not important. If like, for example, if you are focusing on the terminal D and E, you can remove the other terminals like A, B, C, because they are actually connected to nothing, right? So and you drag the D out, and you drag the E out, and then the middle part will be this part, and D and E on the left, right?
Oh yeah, I see that now. Yeah.
Yeah, great.
Thank you.
So just some tricky
Yeah.
redrawing.
So,
Yes,
sorry, I
yes.
had a follow-up question.
Sure.
So do you recommend for each terminal set, do you recommend redrawing the picture? Because like I know
Sure. I
on the first
definitely
midterm,
recommend it. Yeah, because
there's like
when
6 of them, which was kind of tedious to redraw each time.
you're not required to redraw it in the
Right.
exam, right? As long
Yeah.
as you're clear with their relationship, yes.
And
So
also on the sorry,
mhm.
for once we find the equivalent inductance, should we compute it as well, or is it fine just to leave it written out like without the?
That's a great question. So during grading, if you give the correct expression, you get points. But you cannot get full points, right? Because it's unfair to the people that calculate the values. So if you're hurry in the time, get the expression first and then return to it when you have time to compute.
Okay, thank you.
Yeah, great. Okay, let's move on. Check your understanding question. What if C is in series with other elements, for example, resistance here? Can we still apply the parallel? For example, you see that C1 and C2 are parallel. Can we apply the parallel equations here? Just give a quick guess.
No.
Hi,
Guess is
Luca.
no.
So the answer is no. We cannot do that because it is not a clean parallel capacitance. In this case, so we are not required to compute the equivalent capacitance and equivalent resistance here. But in a circuit, we may encounter this situation. And then we have to do the network analysis, like the node voltage, mesh currents, or divisions, as we did before. So I have an excellent example on this situation in the last discussion, and if you have time, you can check it out later. But it is not the most important in the exam, so don't spend too much time on it. Let's go to next questions. It's about all the properties, current, voltage, power, and energy of capacitance. So as Professor mentioned in the lecture, we care about two things about this. The first one is a transformation between the graph and the expression. You should be confident and comfortable to take computation on when you are given a graph or when you are given the expression, like for example, like Vt equals to 5 volts at this time period. So you see that the blue curve match this equation, right? And you should be comfortable with both of them because you may be asked to sketch it or take integration or derivative based on a graph or the expression. So usually we'll see two kinds of graphs. The first one is a square waveform, and it's intuitively you just split it in time domain and then read the values. Okay, and for the triangular waveform, it is a little bit tricky, but as long as you apply the kx plus b, the form of the linear, or we say affine function, we'll be able to get the expression of the waveform. But sometimes if we only care about integration or derivative of the curve, sometimes we don't need to get its expression first, because if we have a if we have an expression, we can use the equation here to derivative, right? It depends on what we care about. But sometimes we can also use some trick on the graph itself. As you may notice, the integration of the waveform is actually the area of the curve. When you have positive values, the area contributes to a positive component in the total integration, and when it is negative, it contributes to a negative components in it. And as for the derivative of the waveform is actually the slope of the curve. Does it make sense?
Yes.
Nice. Yeah, but one thing to be careful about is if you want to apply the graphical trick to calculate, keep an eye on the parameters, the coefficients before it. Like we have a c here, a 1 over c here, and we also have an initial value here, right? So if you want to make sure you don't make any errors, the safest way is still to do it in the equation form. But yeah, it depends on your preference. And here is a check your understanding question. If this graph, the blue curve, describes a property of capacitance, is a blue curve, which is a square wave here, is it at IC or VC? Can we determine it?
BC.
Why?
Or no, IC, I mean, because VC has to be continuous.
Exactly. So we can see that the VC is an integral of IC, and IC is a finite value. Therefore, VC must be continuous. So yeah, it's only possible that IC is a square wave here. Okay, well done. Let's move on. Stop me if you have any question. Don't feel shy. Okay, because inductance and capacitance has many things in common, so I put it right below the capacitance one. So the same, we still have graph, expression transformation requirement, and the equation. In the equation here, we still need to keep in mind that there is an initial value, similar, very similar, right? So similar, check your understanding question too. Is a blue curve, which is a square wave here, is it IL or VL?
VL.
Yes, you're right. Because IL has to be continuous. The continuous property is really important because it helps you determine its status before the switch turns on or off. So in a such short instant before or after the switch takes an action, the VC is continuous, so the time is too short for it to change rapidly. So the VC 0 minus, which means the instant before the switch take an action, is always equal to VC 0 plus. And for the IL, it's also always the same. Okay. And check your understanding question 2. What if we are given IL of 10 seconds instead of its initial value? What should we do? suppose we want to compute the expression of for IL of t, to compute IL of t. Give a bold guess.
Integrate the VL.
Yeah, plug it into the integral equation
Right. So yeah. So
and solve for
we
the
should.
unknown.
You're right. Let me write it down. So we should change the equation to t0 to t, and t0 here is 10 seconds, right? So this equation is not fixed. It does not have to be 0. It can be any starting point in time domain. So if we say the switch opens at when time equals to 10 seconds, we can still solve the problem. But this time, our equation on the left becomes IL 10 minus equals to IL 10 plus. They're basically the same, right? Just a shift in the time domain. It does not change its behaviors. Okay. So if you don't have any other questions, I will
One
move on.
question.
Sure.
The stored energy equations for inductor and capacitor, can we always use it, or does the like for inductor, does the current at 0 have to be 0, or can you always use it?
Great questions. So we should notice that the IL here is actually a function. Okay. So if your IL shift in time domain, the same thing will reflect in the energy. So you don't need to worry about that. You asked a great question. So the energy equations is derived based on the assumption that the initial value is 0, but it is applicable for all cases.
Okay, yeah, that was exactly my question. Thank you.
Yeah, good question. So make sure that you don't only put the final like IL infinity is steady state into it. IL is a function, and in the homework you see that the energy is also a function of t. Okay.
Yeah, thank you.
Yeah, and PL is also, the power is also a function of t.
And is the WL is always positive, right? Because it's squared. Or
Yes.
is that not true? Okay.
Yes, you're right. Let's go to the RCRL part. So when we say RCRL, that means that we only have one capacitor or one inductance in the circuit. We may have multiple, but finally they can be merged into one. We said that they are first order because, as we've seen before, both the inductance and capacitance introduce an integral or derivative, right? So that creates a derivative of the unknown variable. That is why we get a first order differential equation. So there are two important factors in this kind of question. The first factor is the switch. In the homework, you see a lot of switches. And the switch effects, what the experiments will react after the switch opens or turn off, it is discussed in detail in last discussion. And you can take a look at it. But the main idea behind that is it's a continuity of VC and IL. Always keep that in mind and you'll be fine. Okay. And here I provide several shortcuts. It is discussed in the lecture also, but I want to on it. So usually there are several cases. The first case is if C or L is not initially charged, we say like we know initial value is 0. This is what you often see in exercise. Okay. Yeah. So in this case, we know that when the switch turn on, when the switch turn on, there's nothing in it, right? It's just 0 here. And after the switch turns on, it will finally reach a steady state, right? Go through some difficulty and finally reach the plateau, right? And the response here is called transient response. And to understand it more thoroughly, this is actually the XC, the complementary solution, and which is a transient response. And after you solve several exercises, you may find something in common. That is, when we try to solve it, we'll see that the solution is always in such a form. So here is a so we are discussing the DC situation. And the V infinity means its final value, its steady value, because we know that after a long time, which means it is steady, the capacitance will finally become an open circuit, right? The inductance will finally become a short circuit. That is because for capacitance, when it is reach its upper bound, no more electrons is flowing to the plates. So that means no more currents will flow at both ends of the capacitance. No current, so it acts like short circuit. Okay, and for the inductance, because as time goes by, it is steady and no more change in the current, because the voltage is a derivative of current. So when we have no change in current, we will have zero velocity. Zero voltage. And zero voltage means that it acts like a short circuit, right? That is 0 plus is 0 plus, as we discussed just now. And the tau here is a time constant. Time constant. Okay, and similar for current of the inductance. Also, this is steady, this is I0, this is infinity, blah, blah, blah. All right? And because IL and VC behaves in the same way, so I will use the X here to replace them. And when we know that the C or L is initially charged, and now after the switch takes an action, it is discharging and delivering its power, its energy to the surrounding resistance, and until the resistance consumes all the energy. In this case, this is just the opposite. It has some value at the beginning, and then it drop to 0. And the transient response acts like a exponential function. Yes. And here, actually, we are still using the equation, but we can simplify it. Let me write it down first. Infinity value plus 0 plus minus x infinity t over tau, right? In this case, we know that the infinity value should be 0. And to simplify it, we get 0 plus x, 0 plus minus 0 times the exponential, right? And what we get? We get this. In this case, it's usually seen when a capacitor is charged for a long time and suddenly you turn a switch off and it starts to charging the resistor. Okay. And these two cases are typical, but they do not cover all the situation. So you may already see in this figure, we have many situations because we don't know the layout of the circuit, right? It can be anything. So before the switch turns on or off, the initial value might not be 0 and might not be Vs. It can be something like, for example, we have a Vs here. It is not a very good example, but yeah, like this. Suppose it is 1 omega, this is 1 omega, and Vs equals to 2 volt. And we know that when it gets steady, it should behave like this, right? And the voltage division here should be 1 volt, right? So we know that the Vc initially is 1 volt instead of Vs, right? Not Vs, right? So your initial value really depends on its initial situation in the circuit layout, in a specific layout, right? We cannot always say that, it is fully charged, so its initial value should be Vs, right? That is not correct. You need to analyze the original circuit a bit to get the result. And then suddenly the switch turns off. So the Vs is no longer delivering power to the resistance, right? And what we have here is a hanging 1 omega and a parallel 1 omega with. Actually, we can see they're in series because no currents flow in this way because it is already cut off. And what we have is this loop. And now because energy element, the capacitance already have some energy inside, so it starts to help the resistance, right? So in this case, it starts from 1 volt, and then finally the resistance will consume all its energy, so it will go to 0. Okay. And in some case, it will be charged. It will be charged to an even higher capacitance voltage. And we also see this in the homework. So I assume you got what I mean. Okay.
One question.
Sure.
A little bit up, you have like on like just tiny bit scroll up on the page you were on. The x's in that formula is x
Where?
that right there, that formula, like x of t equals.
Okay, here.
Is x v of c and I of l.
Yeah, x replace.
And it's only those two, right? It's not like v of l or something, right?
You're right. You're right.
Okay.
Yeah.
Thank you.
Good question.
for that example you just showed, where you said the initial voltage of the capacitor is 1. So we just get that by analyzing the circuit and using like voltage division laws right there? Is that,
So
is
in
that
this case, we apply the voltage division law to
Okay,
get the, yeah, you're right.
Okay, cool. Makes sense.
I hope we don't have too complicated circuit in the exam. Okay, so, sure.
Can you go back to the equation, the two equation? Yeah, you highlighted. So my understand is, can I use these equations if the V source is sine or cosine?
Great question. So, I don't think we can.
So we can use only V source is a number.
Yeah.
Okay.
I said we can't because for sinusoidal situation, the steady state is in a similar form of sine or cosine. So it is always oscillating.
Okay.
So that's not on this test though, right? That's the new
For
material.
first order.
Yeah.
For first order, it may happen. If that happens, don't use this shortcut.
Okay. What's the full procedure? Again, can you
Let's
go over
take a
that?
look at the previous discussion. So here
all
is,
of this. Okay.
yeah, here is what we usually see, right? And then we can write down the differential equation of the variable you care. And then we can solve it by the differential equation techniques. And it is not that difficult because we only have two situations. The first situation is DC circuit. And for the DC circuit, if you're confident enough or you're short in time, you can use the shortcut techniques I introduced just now. And for the AC situation, which means that the Vs here is a sine or cosine function. In this case, we split the x into xp and xc, and then we solve it one by one. For xp, we are given this form: a times cosine wt omega t plus b sine omega t. And a, b are unknown here. And why we decided in this format. So a thing you guys need to keep in mind about the differential equation is that for differential equation, we first guess the format, the form of the solution. And then we give some coefficients, unknown coefficients to the form. And then we substitute it into the original equation and solve for the solve for the parameters, unknown parameters. It is not like what we do with traditional equations. We move the terms on left or right, we divide something on both sides, and we finally get a solution. So that is a little bit different. For differential question, you need to observe the format, observe the equation, and then guess what the solution should be. And here we guess that the solution should be in the form of cosine or sine. So we give parameters a and b to it. And then we substitute it into the original differential equation and solve for a and b. After we know a and b, the xp is known. Does it make sense?
Yes, thank you very much.
Good. So yeah, I know it takes some time to digest about how to solve it. So you can check out the previous discussion. If you have any other question, you can refer. You can send an email or PS or whatever. Yeah. And for the XC part, it is basically the decaying term. And we also say it's transient term. And it is always in the form of K1, which is an unknown, E minus T over tau. And this transient term will disappear if the time is long enough. So it's like, I know our initial state is here, and I know our final state is there. And the transient terms is like, is to describe how you reach the final state from the initial state. So this term is important, but it will disappear as time goes. The first term, the V infinity, is actually the XP. If you solve the differential equation step by step, you can prove it yourself. And then the second term, something times 2 minus T over tau, this is the XC. And you plus them together, you get the final solution. So I recommend you, I'm sorry?
Go ahead. Sorry.
Yeah, I said I recommend you to use the shortcut in 2 cases. The first case is that you don't have time to compute the differential equation step by step. The second is you just can't understand how to do differential equation and you want to get some points, and this is your second strategy, because if you don't understand the DE and still use this solution, it can be right sometimes, but it can be wrong. Why it can be wrong? Because as we said that it have many flexible cases. Only when you fully understand what the situation is, you can get the correct values for this too. So yeah, that is my advice. Go ahead. You had a question just now.
So what exactly are these 2 shortcut cases? Is it when it's a series circuit only? When it's like RL or RC and it's just the R's in series with the capacitor or the inductor? Is that what the shortcut case is?
Great question. So actually, it is applicable for many kinds of circuits, no matter it is in parallel or in series. So it depends. So whether it is parallel or in series, what it determines? It determines how you get the infinitive voltage and the 0 plus voltage. So the layout of the circuits, as I showed before here, they will decide how you get these 2 values. Okay? And it also affects how you compute tau. So what you see is a equation here, but actually the circuit's layout, the components relationship, they're all reflected in the terms. Does it make sense?
Yes. Thank you.
Great. So so the exam have 6 questions, and some of the question may ask you to get the expression only, like for example, they may only care what is VC of t, and they want the answer. But sometimes they may also ask you to extend it to the general form, the general solution. Like they want to check if you understand the differential equation or not. So in this case, we have to solve it step by step, right? Because we need the general solution. So I'm not going to cover details in the general solution because it is already covered in the last discussion. But the 2 most important concepts here is that the X is split into XP and XC, which is particular solution and complementary solution. This sounds like big words, right? And does not make much sense. So intuitively, the particular solution means its response to the source. Okay? So let's say that the energy, the capacitance and inductance, they can store some energy, right? But they cannot generate the energy themselves. They only store them and then maybe deliver them later, right? So within the circuit, the one who generates energy is the source. The storage elements will always mimic the behavior of source. So the source is like the boss, and the capacitance and inductance will mimic their behavior. And XP, the particular solution, actually describes how they mimic the source. Okay? In the general form, the FT is related to the source. XP is in similar form as FT, which means that it wants to mimic the behavior of the sources. Just like we said before, if the source is a constant, which means it's a DC circuit, the XP should be a constant too. And if the source is in sine format, the XP will also copy its behavior and also in the format of sine or cosine. So it is a good way to verify your answers. If your answer is not in the same format as a source, the XP is not in the same format as a source, you're wrong. And you maybe recalculate it again. Okay. And the second term, the complementary solution. It also sounds like a big word, but basically it describes how the transient response looks like. As we said before, the transient term is a term that describing how you reach the final state from the initial state. So it would disappear as time goes. If you observe its format, you'll see that it is a exponential function with a minus t over tau, right? So it would decay as time goes. And after several tau, it will reach approximately 0. The XC will disappear. And it is dependent on the circuit elements. How many R you have there, and you have C or L, whatever. So after this, I will go to the last problem in this discussion, which is how to calculate the tau correctly. If you can correctly calculate tau, you are very close to the correct final answer. Okay. So if you are still confused about how to compute XP, XC in different cases, check the last discussion or textbooks. All right. Any questions?
I have questions.
Good.
So we already know the form solutions of the complementary always constant time.
Right.
Right. But the source depending on what the form of this. So if we given sine or cosine, so we know this should be A times cosine plus B sine. But
In XP.
Yeah, in XP. But
Yeah.
what happened? We're given different kind, not cosine or sine. How do we know solution of XP? General.
Yeah, you asked a very deep question in maths. So the differential equation is actually a big family. And so we see that this is a general form of the equation, right?
Yeah.
We said a big family because the FT can take so many possibilities. So here we only consider when FT is a constant or a sine form. So this is what we consider in exam and even in this quarter. For ft equals to other formats, so what mathematics scientists they do is they observe the form and guessed what kind of xp will satisfy this equation, like the derivative plus its own equals to the ultimate goal. So that is by observing and trial and error. Then they give a full table about what you should guess when you have such a format of ft. So if you're curious about that, you can check the table of differential equation solutions and find out. So here I'm not an expert, and I can say that we will not encounter such cases in the exam. Does this help your question?
So in the exam, they just two form, one is constant and sine or cosine, right?
Yeah.
Okay.
Yeah. And in the last office hour, Andrew inspired me. So let's do this check your understanding question. If cosine 100t, how should we solve the problem? Take a guess.
You have to really long particular solution or guess one. It'd be like a plus. Is that what you're talking about, or no?
You're right, but there is a cleaner way to do that.
Oh, I don't. Yeah.
Jake, do you have any idea?
I think you have to. I think you can add the solution, like particular solutions, like you do the constant solution and then you can do the sine and cosine terms together.
Okay, so could you tell me what terms are going to, how will you split them? Let's say f1t, what should it be?
I think f1t is equal to 5, and then f2t would be sine of 2t plus. Well, I think.
Can I put sine and cosine together? Because we know the solution have two terms, sine and cosine.
I don't really remember actually.
Okay, it's a good guess.
I think you can.
So, so Navid said that maybe we can give a long guess of xp. That's right. That is right. And but it is not easy to do calculation, right? And Jake said that maybe we can do it conversely. We can split the ft, and that is what we usually do. And here we make 10 in sine or cosine component. But actually, this is not right, because sine 2t and cosine 100t, they have different omega. So they should be treated as two different equations. And intuitively, sine may look like this, and cosine 100t may look like this. And their frequency is very different. So before we go into chapter 5 and know how to converge two sine function using the sinusoidal series, before that, and it's, for example, if we have 2 sine 2t here, we should put 2 here, right? It still belongs to the term of sine. Yes. And for the f2t, we should guess xp2 with the same omega. So it should be a sine 2t plus b cosine 2t. And for the f3t, we should have xp3 equals to a different a. Let me name it c. C sine 100t and d cosine 100t. Does it make sense?
Yeah. Yeah.
Great. Okay, let's go to the last question. So check your understanding. What we discussed the circuit we discussed before only have one resistance, right? What if we have several resistance? What should be the tau? We know that the tau is RC for capacitance and L over R for inductance. So what should we do if we have several resistance? Feel free to unmute.
Thevenin resistance.
Yes, yes. So we cannot simply calculate them by, oh, I noticed that there is an R1, so R1C might be tau 1 and R2C might be tau 2, and I get them together. That might be correct in some cases, but that is a gamble. So let's fully understand it. If our capacitance is connected in this way, we should take the two ends of the capacitors F terminal to A and B and all the rest in the box, and then calculate the Thevenin equivalent resistance. And I recommend you using the zeroing technique if there is there is only independent source. Okay, so let's guess. Don't guess. Let's compute. What should be the equivalent resistance in the first figure? Zeroing means the Vs is 0 now. If it is 0, that means it becomes
R1
a
and
wire,
parallel with
right?
R2.
Exactly. So it should be R1 parallel to R2. After you get your resistance, compute the new tau with R equivalent C. So the XC terms, if you need it, should be the T over this tau. Okay? So you'll see that all the resistance and the relationship between the resistance are reflected in the tau already, right? Because if they are in series, the tau will be different. So back to your question before, you asked, does the layout affect how we calculate it? Yes, it affects, but it does not change the equation directly. It changes the terms in it. Does it make sense?
Wait, so just to clarify, in the shortcut equations, when you had like I or V of infinity, that was like you said that was like the
Steady
particular
state.
solution?
Yeah.
Yeah, okay.
Yeah, you're right.
Okay.
So in this case, when it reaches the steady state, this is taken as an open circuit, and its voltage should be equal to the voltage across resistance 2. Let's take a look at the second example. Now we have a inductance. How do we calculate the Thevenin equivalent resistance? So we use a similar trick like dragging the element out. We drag the terminals out and put the rest of the circuit in the box. Let's see how I do it. So it is easier to do it on a tablet. Let's drag. Oh, drag it. Huh? Okay. Some accident happened. So I drag it from its original place to the outside. The same, right? I didn't do anything to the circuit, actually. And then I put all the things looking from the terminal A bit into the box. Okay, and I look from this direction. Now I do the zeroing techniques again. And this is 0. So it becomes a short while, we'll see that the R3, R4, they are still in parallel. Right? Does it make sense? So when we compute the tau, it should be this. Right? Let me know if you have any questions.
So this just solves tau if we're using the shortcut method, but like if we need to solve the differential equation, like can we still do it that way? Like set up like, I don't know, use node voltage or something to solve the differential equation.
Great question. So even when you solve for the differential equation, you still need the tau, because tau, we suppose that tau is known. If we are given the circuit layout, we assume that tau is known because you can use your understanding of a circuit to compute the tau. For example, here, if we try to solve it using the differential equation techniques step by step, the XC, we give it a form of K1 times E minus tau over tau, T over tau, right? And here we said that the K1 is an unknown, but tau we said that it is unknown. It is known. And we solve the K1 by using the initial state. Here, we got it. The initial state is known, and x0, we use x because it can be v or it can be I. With x of 0 equals to xp, because we already solved xp, and then we solve xc. So this is known here. We substitute the t equals to 0 here. And then the k1 is the only unknown in this equation. And we also know tau from the circuit. That is why we can get the remaining K1 with only one equation.
Okay. I just was saying like back in lecture, we were able to like, we said tau was,
yeah, you asked a
like
great
1
question.
over tau was S.
So I should take a note
like,
here. We already compute. We already solve tau here. Ooh, okay. So here is all the content of the review, but we have another part. Sorry, it's a little bit over the time limit, but if you have anything else to do, feel free to go, and I will continue with the tricks for the midterm. 2. Okay. So for preparation, I'll split it into preparation and during the exam. So because when we are in the exam, we're usually nervous. So it will always be good when you're preparing your cheat sheet, add conditions inside. For example, when we try to use the zeroing technique, we said that no dependent source. Only when there is no dependent source we can use it, right? So and as you mentioned just now, like tau, you say that should be computed before we want to solve XC, right? It will save you from the desperation when you just can't get the answer during the exam. So in the cheat sheet, add the conditions. And preparation 2. Go through your homework solution. So I will release the homework 4 solution tomorrow morning for you to prepare the midterm. And our solution always includes the steps. So it's always good for you to compare your step with their step, because sometimes you get the correct result, but maybe it is just luck. Maybe you ignore something, but that did not affect the result in this exam, but maybe it will affect in the exercise, but it may if affect in the exam. Yeah, you got me. I'm a little bit wordy. Okay. And the third is, because time is short, make sure you in the above question, among the 6 question, because sometimes I myself usually start reviewing the things I'm most familiar with because I feel comfortable, I feel confident, and I'm scared to start with the most difficult part. But it turns out that the things I know, I always know, and the things I don't know, I need more time to digest it. And it's called marginal benefits, right? If you put your time in your most familiar part, maybe you can solve the first 1 or 2 question in the big question of that part, right? That would get you like 10 more points maybe. So you can spend some time to strengthen your understanding on your familiar part, but make sure you have some time to prepare for your most unfamiliar parts, right? You will feel frustrated during your preparation, but it will pay off when you feel less frustrated in the exam. Yeah, I hope it makes sense. And during the exam, that is what I want to stress more about that. The first point is, from the perspective of the grader of myself, I want to give you as many points as possible. But sometimes some of us did not manage time properly enough, so they just skip the whole question, right? If you read our grading policy in the grade school carefully for the midterm 1, you'll see that I give points for every sub-step in the question. Like, for example, if you can draw some figure, what happened to my pen? If you can draw some figure of the equivalent circuits, whatever, right? If you can draw it, or when you compute tau, whatever, you get some points, right? And if you write some equation that helps solve the answer, helps solve the problem, you get points, right? And for the switch, for the circuit with switch, we need to analyze the status before and after the switch opens or close, right? Even if you don't get the final result, you at least show your understanding about the continuity of VC and IL, right? There does not change between and after the switch. Take an action. And you also get points. And no matter for the differential equation, the general solution, or the shortcut, even if you did not get the value, at least you write the expression, show that you understand it. Okay, you just have no time to compute it. right? If you have expression, I know that, oh, at least you understand how to solve it. You just have no time. I'll give you points. So, or the main idea behind is that before you solve the question, before you write down all the process of your long process, long calculation, the main idea is that think clearly about what steps are you going to take. You're going to take. And think about what techniques, what knowledge the professors want to check our understanding on, right? You get clear what steps we are going to do, and you sketch them or something. You just split it, and then fill out as many blanks as you can. Okay, because we always appreciate the solving process, the problem solving skills, right? So even you get too nervous or the time is too short for you to cover the problem, or you're just too nervous and forget everything about that, don't leave it blank. Write down something. Show at least you understand this, just like in the interview. If someone asks you a question and you don't know how to solve it, don't just keep silent. Try your best to say that although I don't know the exact solution, at least I know what is this, what is that, and I'm going to solve it using this equation or maybe that equation, or I have a diagram for analysis like this. But in the answer sheet, you don't need to write down the sentences I said before. You write down equations, you draw figures, you give some expressions, right? They all show your thinking about the problem. Okay. Yeah. And the other thing, also the last thing, is that so the time is short for everyone, and every year maybe. I want to write this down, because sometimes you may get unconfident during the exam, and you see others finishing their papers so early. But what I see from the back end is that time is short for everyone. Even the students that master the materials very well, they also have this problem. So you'll see that at the beginning, their writing is very good. And as time goes, it becomes more and more unreadable. And this makes sense. And maybe they will get some calculation error at the end of the midterm and just give up. So this happens. Just keep in mind that everyone have the same situation, and don't stress yourself too much, and don't blame yourself too much. Just keep calm and try to solve as many as you can. I hope this discussion is helpful to you and good for your preparation. Let me just say best of luck next week, and feel free to reach out in Piazza or email or schedule extra appointment if you would like to. I'm always willing to help, and I really wish that you achieve something from this course, and I really hope you get a good result out of midterm too. Thank you.
Thank
So
you.
I will stay. Yeah, thanks for your question too. I will stay until 2:30, because today's discussion starts later than usual. So if you have any further question about homework, midterm, or the contents just now, just feel free to ask me. Thanks. I will stop recording right now.